Hi, how are you? This is my English speaking practice and I'm working on coding problems for a while. Today's problem is linked list cycle. This is like my rehabilitation. Rehabilitation. Yeah. Rehabilitation for coding problems because it's been a while. So I'm gonna solve this one easy level. Given the head of a linked list, determine if the linked list has a cycle in it. There is a cycle in a linked list if there is some nodes is in the list that can be reached again by continuously following the next pointer. Internally, pos is used to denote the index of the node that tail's next pointer is connected to. Note that pos is not passed as a parameter. Return true if there is a cycle in the linked list, otherwise return false. So this case, this is a linked list and we are given the head node of the linked list, and we can run through this linked list because the node has a next pointer, and in this case this node has this node's next pointer point to this one, so this linked list has a cycle. So in this case we have to return true, right? And what is POS? Internally, POS is used to denote the index of the node that tail's next pointer is connected to, but it's not passed as a parameter. So we don't need to think about this one because we cannot access it, and yeah, and if it's not -1, obviously there is a cycle because POS definition is like this: used to donate the index to the node that tail's next pointer is connected to. So yeah, so what we're gonna do is to find the cycle in the linked list, and we are given the head node. So basically we are going to run two pointers, faster pointer and slower pointer, which means for one step faster pointer moves twice and slower pointer moves once. So for one step there is one difference, the pointer move, and if we repeat this procedure, the faster pointer can reach to slower pointer, right? If there is a cycle, right? Let's see. So for the step 1, the pointer starts at head node, and after the step 1, faster pointer is placed here and slower pointer is placed here. For step 2, the faster pointer comes here and slower pointer comes here, right? And for step 3, the faster pointer come here and slower pointer come here, and which means the faster pointer reach to the slower pointer, right? So we can figure out there is a cycle. Yeah. How to implement this? So faster pointer, slower pointer is located and we are going to loop it. There is an edge case. If the head node is none, there is no list. If there is no list, obviously there is no cycle, so return false. And how about that the head node, the next pointer point to the head node itself? I think that is also that is a kind of cycle. So if the head node doesn't have the next field, should return false. We should return false. And as the initial state, the first pointer should be at next, next, and throw a pointer is next, right? We can make sure there is a next node. There is a next node, so so we can initialize like this. And at the time, the pointer might be the same. So in this case, return true. Right. And after checking the pointer, we move the pointers. So faster. Faster pointer. Might be none, right? If it's none, there is no cycle. If it's same as slower pointer, there is a cycle. And after checking, we move forward. We move forward for 1. We move the pointer. We move the pointer forward. And every time we move forward, we have to check it. Right? And finally we advance the slower pointer forward. Is this... I'm not sure. Let me see the result. Not bad, not bad. Constant memory. This solution is already solving in constant memory, right? So yeah, so there is another naive solution. It's like using set or something, and we can store the memory address we visited. For example, look at one by one and store the memory address. This one, and when we revisit here, the memory address is already stored in the hash set, so we can find out there is a cycle, which is a naive solution, because not naive, but it's not best solution, because we can solve this problem in constant memory. So this solution is memory effective, I think. But I'm thinking about the edge cases, or I'm not confident about this. Move the faster pointer twice. Move the faster pointer twice. So in this case, the initial state is like this: slower here, faster here, and faster pointer move twice at first, here and here. And so at this point, faster is not none. Faster is equal to slower pointer, so return true at this point. The number of nodes in the list is 10,000 at the most, so Hmm. So at most, faster pointer will run through the linked list twice, because if the first pointer run through the list twice, the slower pointer is about to finish the first loop. So it's not bad. Okay, great. Not bad. But I'm curious about I'm curious about the expected answer, and yeah, I think this is almost same. Initialize and move first, move twice. Maybe this condition is too much. I'm not sure. Because I wanted to avoid the matching situation. What I want to say is like faster pointer here and for example, slower pointer here and faster pointer here, and move twice, like so the faster pointer move once, the condition they meet here. Move once, move twice. Walker moves step by step, runner moves 2 steps at a time. If the linked list has a cycle, walker and runner will meet at some point. Two, 2, 3, 3, 5, 4, 4, 1. Yeah, this case this case is good. How about this case? Six and one. Oh, this case is also good. Oh, I see. Oh. Okay, so the distance between slower pointer and faster pointer is decreasing by one by one. So I don't need to care about the condition where the faster pointer is moving. Because the distance is, this case there are two, distance is 2, and at the next time the distance is gonna be 1, right? And the next, for the next, they meet, so the distance is decreasing one by one, right? So these conditions are too much, I think, so we just first we want to make sure there is a valid node in the linked list. And if this condition is not met, there is no cycle, obviously, right? The linked list is ended, so we can return false. And thanks to this condition, we can remove these conditions, and as we see how the distance is decreasing, we just check like this, and like this, right? This solution is also good, but it's getting slower than before. But it's okay. Huh? This code is more simple, so it's okay. Yeah. Okay, next, intersection of two linked lists. Given the heads of two singly linked lists, head A and head B, return the node at which the two lists intersect. If the two linked lists have no intersection at all, return null. For example, the following two linked lists begins to intersect at node C1. Okay. The test cases are generated such that there are no cycles anywhere in the entire linked structure. Note that the linked list must retain their original structure after the function returns. Custom judge. The inputs to the judge are given as follows. Your program is not given these inputs. Intersect value, the value of the node where the intersection occurs. This is 0 if there is no intersected node. List A, list B. Skip A, the number of nodes to skip ahead in list A to get to the intersected node. The number of nodes to skip ahead in list B to get to the intersected node. The judge will then create a linked structure based on these inputs and pass the two heads, head A and head B to your program. If you correctly return the intersected node, then your solution will be accepted. Okay. The idea that comes to my mind first is to store the addresses we visit. So in this case, we start at for A, and we store the addresses of node we visit. This one, and at the time we can find out the end of the linked list, and then we are going through for linked list B and look at one by one. And when we visit here, this address is already stored in the hash set, so we can return what we should return. return the node, so we should return the address, this one. But there is a follow-up question. Could you write a solution that runs in O m plus n time and use only constant memory? So I want to come up with this solution that runs in O of m plus n and use only constant memory. The solution I explained is runs in O of m and m plus n, but space complexity is O of m, because we need to store all of the addresses for list A. And there is a note that the linked list must retain their original structure after the function returns, so we cannot modify the value. It's not allowed to modify the value in order to record something. For example, modify some value so that we can find out that the node is already visited or not. It's not allowed, so we cannot do that. So append. While next. As long as there is a next. Walker will move forward. And if the address is already stored in the set, we return it. Otherwise, continue to do it. And finally, return. No. How about this? Set object has no attribute. At? I forgot the syntax. Maybe add. Correct. So this solution's time complexity is O of m plus n. Right? But space complexity is not constant because we use this set, and this have to store each address we visit for linked list A. So how to improve? Before trying to reduce the space complexity, let me confirm this solution is correct or not. Correct. And good speed. Ah. Hmm? Ah. If there is an intersection, the last node must be the same. So we just check the last node, right? And if it's same, we should look back one by one. Look up one by one. In order to find out the intersection node, right? So there are two steps for checking. We just look at the last node. If it's the same address, there must be intersection. So maybe I'm sure we can remove this one and this one, and but instead we update the last node. If the head B is same as the last node, its last node, it's not only last node, it's but also the intersection node. This is an edge case, and for normal case, last node B. We are updating the last node B. It should be like this, and after walking through the linked list B, the last node should be same as the last node A. Otherwise, return false, because the last node is not same, right? there is no intersection, so we just return none. And so let's think about this case. We can find out there is same last node, so there must be intersection. And how to find out the intersection? We have to look back. We have to look back. But this is singly linked list, so it's difficult to look back from the end. Inconstant? Really? I cannot come up with a solution. What? Visualization of this solution. Let me read. I found most solutions here pre-process linked list to get the difference in length. Actually, we don't care about the value of difference. We just want to make sure two pointers reach the intersection node at the same time. We can use two iterations to do that. In the first iteration, we will reset the pointer of one linked list to the head of another linked list after it reaches the tail node. In second iteration, we will move two pointers until they point to the same node. Our operations in first iteration will help us counteract the difference. So if two linked list intersections, the meeting point in second iteration must be intersection point. If the two linked lists have no intersection at all, then the meeting pointer in second iteration must be tail node of both lists, which is null. Visualization of this solution. Case 1 have intersection and same length. So step 1 by 1 we met. Since okay, have intersection and different length. So this case A comes first, and A reaches to the end, and the pointer A come here. I see. Notice that if list A and list B has the same length, this solution will terminate in no more than one traversal. Yeah, if both lists have different lengths, this solution will terminate in no more than two traversals. In the second traversal, swapping A and B synchronize A and B before the end of the second traversal. By synchronizing A and B, I mean both have the same remaining steps in the second traversal, so that it's guaranteed for them to reach the first intersection node or reach node at the same time, technically speaking, in the same iteration. See case 2 have intersections and different lengths, and case 4. There are many great explanations of this solution for various cases. I believe to visualize it can be solved most of doubts posted previously. Makes sense. So if they have different lengths, so this case 5 and 6, we just iterate twice, because this pointer go through 5 elements for the first iteration, but the second iteration it's moved to here, so 5 plus 6. So this pointer are experiencing 5 plus 6 nodes, 11 nodes total. And likewise, B at first experience 6 nodes, but for second iteration it experience 5 nodes, so 11 nodes total. So yeah, if there is a intersection, have intersection and different length, in the second iteration the two pointers will meet. That makes sense and so smart solution. Okay. But my solution is not bad. The memory usage is not good, but accepted, so I think it's not bad. Okay, let me solve one more. Given two strings S and T, determine if they are isomorphic. Two strings S and T are isomorphic if the characters in S can be replaced to get T. All occurrences of a character must be replaced with another character while preserving the order of characters. No two characters may map to the same character, but a character may map to itself. Okay. So this case, S is egg and T is add. This is true because E can be replaced to A and G can be replaced to D. But this case is false because there is two ones. This is different characters. So the strings S and T cannot be made identical as one needs to be mapped to both 2 and 3, right? Paper and title, this is true because P can be mapped to T and AER is mapped to ILE respectively. There is a constraint. The length is 5 times 10,000 and the length is same. Constant of any valid ASCII character. Okay, I see. Isomorphic. So we gonna use default dictionary mapping, in other words, and the character in S Yeah, character in S. If there if the mapping has already the character in S as a key, if it's not same, it's impossible, right? And otherwise, we have to update the mapping, and after the loop we just return true because all checks are passed. Alright? I think so. Char is not defined. Oh, really? Char. Not char. String. Great. Is there any edge cases? It's good. Seems good to me. Wow, wrong answer. BADC. Opposite mapping. So I mean A and BADC. So B is mapped to B at this time. And when D comes here, it shouldn't be mapped to B because B is already used here. B is mapped to B, so we cannot use B here. I don't care about this. So the mappings in the opposite way, opposite direction. This mapping is S to T, and this mapping is for T to S. Right? So mapping 2 uses TC as a key. So SC is the value. And yeah, so mapping to TC is not same as SC. Return false. And otherwise mapping 2 is updated like this. So thanks to this part, B is mapped to B and A is mapped to A, and when we get B again here, this condition is true and this is B because it's mapped to B, but the SC is D here, so it's not good. We can return false, right? And AC is as well. A is already mapped to A, and when we get C here, so it's not good. But this direction, it's allowed because B is mapped to B, A is mapped to A, and D is D comes at first, so D can be mapped to anything this time. So this is true, this is valid, this is valid, this is valid. So we cannot detect this case. So this is good. Great. Isomorphic. Okay, so yeah, I solved 3 problems here, 3 problems today. It was a good rehabilitation. Thank you for watching. See you.